Okay, good morning, everybody. I'm glad everyone could, or many could make it so early. 8:30 starts, very Swedish, I guess. We've got three great keynotes this morning. I'm very sort of excited. I guess I was one of the ones that suggested these three people as keynotes, so I'm very lucky to be able to chair the session. We have Sabine Fuss first, Detlef van Vuren, and then Oliver Gedden. And we may as well just get straight into it. So Sabine, many of you may know already, she's probably one of the only economists here. She has a background, I guess, in, there's another economist, I know, a couple, in decision-making in uncertainty. And one of her first papers was called, or first papers on negative emissions was called Betting on Negative Emissions, which is sort of appropriate title given the background, and it was certainly a well-discussed title, whether we should call it that. Since then, Sabine has written quite a few papers on negative emissions and led quite a few different initiatives. Some of you may know of an initiative through the Global Carbon Project that Sabine has led. She's also involved in the IPCC special report on 1.5 degrees. So she's very busy, very hardworking, as many of you will know, and she does all this while having a baby. So I'm very impressed that you could make it, and really look forward to your presentation, so thank you.
Thank you so much, Glenn, you embarrass me. So a very warm welcome in this early morning also from my side. What I'm going to talk about this morning is what we know and don't know about negative emissions. So those of you that have been present at Parallel Session 2B yesterday already got a preview of this. But I hope that you can also take away some more messages when I go a little bit more into detail today. So yesterday we actually launched a series of 3 papers and environmental research letters that were presenting a very systematic review of negative emissions. And I'm going to give you a tour through these, and hopefully, therefore, also set a little bit the stage for today. So why did we actually think that we had to do this? The reason is that we observe in the climate stabilization pathways that negative emissions technologies are more and more important in meeting the 2-degree target, but also, of course, the 1.5-degree target. And what we see in the literature, and this is from Jan Minks et al. 2017, is an explosive growth in the literature on negative emissions. So the different colors pertain to the different assessment cycles. So we see that for AR6, we will have to cover quite a bit of material. And we were asking ourselves, what we can actually do in order to make those systematically accessible, because there are a growing number of assessments, but we found there's relatively little systematic review work going on. That leads actually to substantial discrepancies when we look at global potentials, costs, and so on. And it is therefore unclear what determines those ranges. Is it expert judgment? Do we increasingly see selection bias? And we felt there is a lack of analysis of the variability in those estimates. So this is why we set out to systematically assess all the literature that is out there on negative emissions. So this review came in 3 parts. The first part was led by my colleague Jan Minks, also at the MCC in Berlin, that looked at the literature landscape and provided a synthesis of the findings of this project. The second one, that was led by me, was really diving into the ranges that we find for costs, potentials, and side effects at the global scale. And the third part, led by Gregory Nemeth, was really on the whole challenge around innovation and upscaling. So this is basically the whole package, but I'm going to walk you through from 1 to 3. How did we actually do it? So we first developed a scoping protocol for this assessment. We identified the literature by designing search queries for the Web of Science Scopus and so on. And we were reviewing those queries together with technology experts in the field and fine-tuning those so that we would not miss any of the literature. And we ended up with over 6,000 documents from the Web of Science and Scopus, and then 270 documents that were added later when we were asking authors, did we miss anything? And also trying to pull from the community more papers. Then in the second step, we did a preliminary scoping review where we screened all the titles and abstracts to see whether they contained the information that we were after. And we narrowed down the literature body to 2,000 documents. And that was the basis for part one. So basically looking at the landscape of the negative emissions literature. We then went on to do a full scoping review where we extracted the information on costs, potentials, and also the side effects, because there has been a lot of debate around the sustainability of some of the negative emission technologies. So we wanted to make sure to also extract that information from the body of literature. And we ended up with a little bit over 900 documents that contained the information that then went into the assessment of paper 2. And then finally, for paper 3, the challenge on innovation and upscaling, there was a keyword and coding rubric established for each innovation stage. All the papers were coded so that it could be established where the bulk of the literature is actually focused on, and I'll get back to that in the end of the presentation. So let me start with part one, the literature landscape and the scenario evidence that we would like to link up to. What you see here is the coverage of literature on negative emissions technologies, and we have actually ordered this in along different IPCC assessment periods. You actually see that they are quite well represented. So this is the first and second assessment report. You see there is quite a bit of afforestation and reforestation, and also ocean fertilization was already covered there. Then you see a larger spread where where also the soil carbon sequestration component is rising. And a little bit of the others is also coming in. Light green is ocean alkalinization. And in the fourth assessment report, even more are coming in. And then in the fifth assessment report, basically all major nets are already covered. And for AR6, we will, of course, still have to see, but we already see now quite a diversification in the literature. So it seems that technologies as such are covered well, but that doesn't mean that they are already established in the scenarios. So I brought you a typical 2-degree scenario just for illustration. And what you see here are the net emissions. So they cross the zero line in the second half of the century. That means at that point we extract as many emissions as we're emitting to the atmosphere, so we exactly break even. And then after that withdraw more CO2 from the atmosphere than we are emitting back. These are graphs that we've already seen yesterday as well. However, it shouldn't hide the fact that if we're talking about deployment and the upscaling challenge that I will get back to later on, we actually have to look at gross emissions. So this light blue part here means that we're extracting already CO2 from the atmosphere, but less so than we're still emitting back to it. But it does mean that these technologies already enter the portfolios in the scenarios. So Now, if we're looking at the feasibility of low stabilization pathways, 2 degrees or even 1.5 degrees, I'm talking here about the feasibility of the models actually being able to reach the target and not about sustainability at this point. Then you actually see that this depends a lot on how fast we are with emissions reductions. So if global climate action starts in 2010, so pretty much yesterday, then even if we limit the deployment of bioenergy and CCS, then we can still reach the 2-degree target. Well, pretty much all the models do reach it. However, if we delay climate action until 2030, then in the sample that we have been looking at, there was little chance of actually making it. If you had unconstrained use of BECCS, still many models could reach the target if you started global climate action in 2030. But even there, for the 1.5 degree target, it was really close. So this is just to underline that with negative emissions technologies deployment in those scenarios, we're not talking about a substitution, not about something where we just offset some emissions because we want to emit for longer, but it comes along with very ambitious emissions reductions already in the short term. So what do we take away from this? And I don't want to dive much more deeply into the scenario literature because after me, Detlef will actually go a lot into depth with respect to that. And there are also some new scenarios that we're very excited about. So delaying global climate action. And here there has been a lot of literature actually showing that the nationally determined contributions, those pledges that have been put on the table by countries in Paris, are not sufficient to put us on a well below 2 degrees C pathway, will actually increase our dependence on carbon removal. We have to be quite aware of that. That does not mean that negative emissions technologies can offset rising emissions. As I was stressing before, it's key to bring down emissions as quickly as possible with conventional mitigation technologies as well. And carbon removal helps us to offset emissions from sectors that are decarbonized less rapidly. So if we're looking, for instance, at transport, air travel, for instance, is something that is very difficult to decarbonize. So on the way to 2 degrees or even 1.5 degrees, there could be some smoothing because you could be taking out some of the CO2. And especially if we're looking at the 1.5 degree pathways and how close it already is achieving it, we can reduce atmospheric concentrations after we overshoot the budget. So this is a little bit a two-part role that negative emissions can play. So how does the scenario evidence that we saw link up with the knowledge on technologies and practices to remove CO2, what I was previously calling negative emission technologies? So in part 2, we were actually looking at the bottom-up literature and trying to come up with a synthesis there. So let me start with costs. What you see here are heat bars of all those studies that we scoped and that we then went through in order to extract the information on costs. And we looked at 7 different negative emission technologies, or actually rather 8 if you separate out enhanced weathering. So we have for afforestation and reforestation quite a big literature on global estimates of costs. And what you see here are the ranges. So you get quite a good picture of the range that costs are lying in. And they start actually relatively low with the bulk of the literature. And the heat bar actually shows you how many of the studies are at a particular cost level. So it gives you an idea of what the literature actually agrees on, whether there is some consensus. And you see that for some studies, like enhanced weathering, you have different peaks in the distribution of costs in the literature, and for others, you have more condensed. The studies are more condensed at one cost level. So also for BECS, the literature has grown quite a bit. So you see quite a few studies here. Others have less cost estimates at 2050 at the global scale. So biochar, soil carbon sequestration, there were relatively little studies. Also enhanced weathering, ocean alkalinization, ocean fertilization. Direct air capture actually having quite a few, but still in the literature being more at the higher end. So if we then go over to potentials, this is also a heat bar. Here we've actually plotted out the medium potential in gigatons CO2 per year that are sequestered. So each dot represents one study, and again, the darker the color, the more of the literature agrees on that particular cost level. So you see, potential level, sorry. So you see quite sizable potentials actually for almost all of those. Also actually quite some studies on ocean fertilization, and also on soil carbon sequestration, where we previously for the costs had less literature. We then actually went on to, because you're actually seeing that this covers quite a large range, we went on to ask experts on those technologies based on the bulk of the literature that we already extracted to come up and identify what they considered to be realistic ranges in order to make it more graspable for people that would use these to make decisions. And these are the ranges that we came up with. So here you have the costs in dollars per ton of CO2, and the potential for carbon removal in gigatons CO2. And as was already obvious from the heat bars, direct air capture, BECS, actually pretty much all of them have quite some potential. The cost structures are quite different though, with BECS sitting here somewhere in the middle, direct air capture still being on the higher edge, and then the more natural negative emission practices on the lower end with soil carbon sequestration, where you actually could even have some studies were even finding negative costs, so it would even make sense to do these things without any climate policy, and then also afforestation being quite readily usable. So we then went on to, as I promised, to also look into other aspects that have been floated in the debate, to extract that information from the papers. And in particular, we were looking at the readiness of the technology, on the side effects, specifically sustainability issues, and also the permanence. So the technological readiness is actually quite diverse across those different technologies. You have things that we have quite a lot of experience with, and where the literature goes back quite a long time. For instance, afforestation and reforestation, but also soil carbon sequestration. Then you have technologies where we have experience with the components, but really for the full supply chain, we have almost no demonstration. So at large scale, so BECS would be typically one of those. And you have technologies that are relatively new, that still look expensive, but that are coming on in niche markets now, such as direct air capture. Now, the side effects are here on the left-hand side. So what we did was that if there was a critical mass of papers in the literature that documented a side effect, we were adding it here. And of course, in the debate, BECS has been very prominent, so let me start with that. The major concern is really about the competition for land in the literature and how that could actually be at odds with our ability to safeguard ecosystems and to grow food for a growing population. On the other hand, a lot of the afforestation and reforestation literature shows that if you do it, if you implement it in a way that is compatible with land use competition, you can actually have positive impacts. However, it also became very clear from the literature that afforestation has a quite high land footprint as well. So the land use competition is not really going away just because we're doing afforestation instead of BECS. Now, for biochar, it also depends how you implement it, whether you use residues, but at that scale where it would probably be used in the scenarios if we were going to do it with one technology, probably you would also have to grow additional feedstock, so that would then also come out as a land competition downside. On the other hand, you do have positive effects at the agricultural side as well. The same is actually true for soil carbon sequestration. Enhancing soil in carbon in the soil is actually good for agriculture. And for direct air capture, the literature was actually really sparse. There was almost nothing on side effects, at least no significant body. So this is also a research gap that we identified. And for enhanced weathering, where you grind basalt, for instance, very finely and distribute it over a forest or agricultural area to then, by chemical reaction, absorb CO2. You have to, of course, also account for the fact that you have to mine all this basalt. So you have also the negative side effects documented quite well from all this large mining activity. So we also wondered whether we should also say something about the longer term, because all of this analysis we did for 2050, but we were trying, by asking again the technology experts, to come up with an indication of where the costs and potential would be evolving to. And just to pick out an example for the trend after 2050 for bioenergy and carbon storage, what we believe is that if we if we exploit more and more of the potential, we'll be running into land constraints, so costs will probably be higher and probably outweigh whatever technological progress we will have had until then. And then finally, permanence is also an issue. So you see those technologies with geological storage, like BECS, direct air capture, where also the CO2 would be injected. These are typically the ones that are thought to be more permanent in terms of storage. And you have at the other end, the more natural solutions, afforestation, reforestation, for instance, where you also have to take into account that either human influence or also ongoing climate impacts could actually adversely impact permanence. So if you think of forest fires, droughts, and so on. So the conclusions taken away from paper 2 are that, yes, we do see relevant potentials for all the negative emission technologies. Ocean fertilization, our expert team didn't feel comfortable coming up with a long-term range for the potentials because of the large uncertainties that were still documented in the literature. Potentials are all constrained by biophysical or economic limits. What I was showing you, for instance, was that direct air capture was at most assessed to have a carbon removal potential of 5 gigatons CO2 per year by 2050, but this is actually not a biophysical constraint, but it's motivated by the assessment of our experts to about the upscaling and the economic constraints. Also, a caveat, potentials, as I've shown them, are not additive. They will be competing for resources, as for instance, land, biomass, geological storage. So they shouldn't be added up and we think, oh, we're fine. They have to be seen in a dynamic setting, or, as is increasingly happening, being integrated into the integrated assessment models. And I'm sure Detlef will actually say something about that. What we believe to take away from this literature review is that any single negative emissions technology is unlikely to provide the potentials that we currently observe in the scenarios, at least not sustainably so. And what we think is that in the future we will be looking at a portfolio of different negative emission technologies, and that if each of those is deployed at a modest scale, we can then actually reduce the risk of adverse side effects. And that brings me to part 3, led by Gregory Nemeth, on innovation and upscaling. And as I said, what was done was to code the whole literature that we got from the first scoping step, alongside the different stages of the different innovation stages. So R&D, demonstration, scale up on the supply side, and then also moving up to demand factors, niche markets, demand pull, and public acceptance. And what you actually see is that a lot of the literature is actually focused on the R&D stage, so very little on a demonstration stage. And then if you look at the demand factors, the later stages in the innovation stage, also very little literature on niche markets, demand pull, and the public acceptance. So more work is needed here as we conclude, and this is really at odds with what we see in the 2-degree scenarios that were available to us when we actually conducted this research. So the upscaling that we actually see in the scenarios is not even reflected in the academic literature, and that should give us to think, I think. Finally, and I'm just bringing this because in session 2B yesterday this caused quite a bit of discussion. We also think that for those different technologies that partially don't have any precedents, we need accelerated models of innovation. And so Greg was comparing the experience that we had with PV to DAX, where actually the first commercial plant or the first commercial application was in 1957 for PV, and by now we can actually say we're arrived at a pretty low cost solutions, and widespread adoption still probably being 20 years ahead. And if we compare that with direct air capture and storage, well, we have Climeworks having gone online with last year with a plant. But then if we translate the PV experience to that, we will be looking at 2076 for the real low-cost options, and then widespread adoption by 2099. Well, clearly, by that time, that's really not relevant anymore in terms of those scenarios. So if we take this thought experiment further, we would actually need a factor of 4 acceleration in order to make that useful for low stabilization pathways. So this is just putting this out for discussion. Let me then get back to the title of my presentation of what we know and what we don't know about negative emissions. What we know is there are actually more technologies out there than BECCS. They have relevant potentials. Not all the literature is specifically targeted at 1.5 degrees or 2 degrees, but a lot of tech practices, for instance, I was elevating afforestation, reforestation. There is quite a bit of experience there. Negative emission technologies will likely play some role in meeting the Paris climate goals, but there are now a couple of new scenarios that were not part of this research and that we will probably be hearing about in the next keynote that limit the dependence on negative emission technologies, but they're nonetheless very ambitious as well. So what we think is we need a societal discussion about the risks to sustainability, about the different trade-offs, and thereby come up with a negative emissions technology portfolio that society feels is feasible. And also, we need to get our heads around the upscaling challenge. There is a large gap between the upscaling we see in scenarios and reality, where incentives are missing. And here, actually, the third keynote will also touch on the policy space. What we don't know is something that is now only happening, the integration of a wider portfolio of negative emissions technologies. Then alternative short-term policies to foster negative emission technologies. Finally, there's relatively little on the political economy and on public finance of negative emissions, and also the ethical dimension. There is quite a big bit of ethics literature that we covered in this review, but it often claims to be referring to carbon removal, but is in fact about solar radiation management, which comes, in our opinion, with a quite different set of risks. So just to also flag some gaps on what we don't know, and seeing that the community is now so large, I'm actually quite optimistic that we can embark on closing some of those gaps in the near future. Thank you.